do another example. I actually enjoy whoever wrote this problem, props to them. So the Great Sandini is a 60-kilogram circus performer who is shot from a cannon, actually a spring gun. You don't find many men of his caliber. So you help him design a new gun. The new gun has a very large spring with a very small mass and a force constant of 1,100 newtons per meter that he will compress with a force of 4,400 newtons. The inside of the barrel is coated with Teflon, so the average frictional force will only be 40 newtons during the 4 meters he moves in the barrel. At what speed will he emerge from the end of the barrel? 2.5 meters above the initial rest position. All right, so the spring, if you have a spring with 1,100 Newton per meter spring constant and you apply 4,400 newtons, well, every 1,100 newtons is 1 meter and 4,400 is essentially 4 of those. So that spring will stop pushing him at the end of the barrel since it said he moves 4 meters inside of that barrel. Okay. It also tells us that the height is 2.5 meters above where he starts, so we could figure out the angle of this launch if we wanted to. Of course, every time I do this one, I'm like, oh, I know the angle of launch. I know essentially the initial height and the velocity. 2D motion, projectile motion. Does he like land in something cool? Oh well, for another day. So we're going to solve this using energy methods. So spot 1 is down here where he starts. Spot 2 is where that he leaves. So let's go ahead and let's write out that work kinetic energy theorem. Whew, I'm getting fast at that. All right. So what is going to cross out for us? So there is no work in, no one is pushing on the Great Sandini. Now, someone did need to push down the spring into this spring gun, but no one actually was applying a force after that. Okay. There is friction, that 40 newtons it talked about. He does have kinetic energy when leaving the gun, does not have kinetic energy at the start. At the end, he does have a height of 2.5 meters at the start 0. So we are going to call his starting height 0. And then the spring is no longer storing energy once it's been released, I guess. So once it gets back to that equilibrium point at the end of the cannon, it's no longer applying a force. And then it does have some energy stored when we compress it. All right, so let's see what we got left here. So we got force of friction dot displacement equals 1/2 mv squared plus mgh minus 1/2 kx squared. All right, so the force of friction was 40 newtons and it is opposite the displacement. So I have a negative 40 times the displacement, which was 4. I have the 1/2 times his mass, which was 60 kilograms, times v squared plus 60 times 9.8 times a height of 2.5 minus 1/2 times the 1,100 Newton per meter spring constant times how far it was compressed, 4 meters. To be honest with you, I just went ahead and plugged this into Solver on my calculator. But if you wanted to, you could add this over to this side, subtract this over, multiply by 2, divide by 60, take the square root, and see what you get. You should get the same number as me. He comes out at 15.46 meters per second. It's like 30-ish miles an hour. So he comes out at 30 miles an hour. That's a pretty good speed for a spring-loaded cannon. So good job, Sandini. What great caliber he has. All right.